compression, RB. The length is 0.3, and the cross-sectional area is 400. Okay. So 0.3 divided by 400 power minus 6 is equal to 750 RB. Then we're going to do summation of forces or deflection due to redundant load will be equal to minus 1200 RBE over E plus by minus 750 RB over E. So it's equal to 120 plus 750 is minus 1950 RB over E. Okay. So what you observe, like what I told you guys earlier, right? The applied load, I hate this one, sorry. So this is plus by 1125. Is it 1125? 540, 360 plus 225. 540 plus 360 plus 225. 1125 times 10 to the power 6 divided by Young's modulus, right? Like what I mentioned to you before, the load and the redundant, the deflection due to the applied load and the deflection due to the redundant load are always in opposite direction, like what I told you guys before. Okay, I want you all to observe this. Is important. Okay. Then from here, you can calculate what is your RB now. Okay, so we are going to apply the equation where delta L plus by delta R is equal to 0. Before I write this out, okay, the key point of this analysis is this, okay. When it is the applied load, okay, you divide them into 4 sections. Okay, this is because of the applied load and the redundant load. Sorry, the applied load and the change in geometry. For the redundant load, you only need to divide it twice. It's only because of the change in geometry, but both of them are going to feel the same redundant load at RB. Okay.
Is that always? Sorry, that's not always though. That's just for this example, right?
Yes, for this example. But what I'm trying to tell you is due to the applied load and redundant load, don't always assume that you divide the section the same way. Okay, so that's where throughout my 15 years of teaching this course, that is a common mistake. Okay, I want you to learn how to analyze this. Really, really important. So we calculate the deflection of L plus by deflection of R is equal to 0. So deflection of L is equal to positive 1125 times 10 to the power 6 over E minus by 1950. Okay, RB over Young's modulus. So it's equal to 0. Okay, so you can calculate RB. Right, so you bring it over, you can get rid of the Young's modulus, so it's equal to 1125 times 10 to the power 6 divided by 1950. So this is equal to 1125 power 6 divided by 1950 is equal to 576.923. Times 10 to the power 3. Now, if it's positive, this is positive, means the direction is correct. Okay, this is positive, the direction is correct. Why the direction is correct? Because we assume the direction RB to be going up. Okay, if over here what you calculate becomes negative, which is impossible. Okay, this value cannot become negative. If it's negative, there's something wrong with your equation. Okay, if it's negative, there's something wrong with your equation. Okay. Why is impossible to be negative? Anyone? Why did I make a statement it's impossible? So it's impossible to be negative. Anyone? Can anyone tell me why? Remember, I mentioned this before, right? Deflection of L of the load will always be in the opposite direction, yes or no? So when you come over here, if this is positive and this is negative, when you bring it over, both are positive, okay? Or when this is negative, this is positive, you bring over, both sides will be negative, then you calculate RB will also be what? Positive. That is the reason. That's why it's impossible to be negative. Okay. So now, we are going to calculate the reaction at point A. Okay, we are going to calculate the reaction at point A. So if I go back to this diagram, I'm going to go back to this diagram. So we know, so if we are, I'm going to construct the free body diagram. Okay, so we know that over here we have a RB that is equal to, we calculated to be equal to what? 576.923. Okay, and then at point A, I make an assumption. We make an assumption that what? AY is in this direction. Okay, why? Because remember, it has to be pushing outwards. Okay, if it's pushing inwards, okay, pushing towards A, means it's not going to stay down, it's going to move. Okay, so for now, we make the assumption that AY is pushing upwards. Okay, so based on static analysis, I'm going to draw our Y transformation on Z. Okay, so to find direction of point A, we apply static analysis. Right, static analysis means anything that's going up is going to be positive in the Y direction. Okay. When we were doing deflection before, our analysis is tensile is positive, compression is negative. Compress.
Sorry, sir. This is probably a dumb question, but why did we assume AY is going upwards? If like I'm using hangman theory, it should be going downwards.
No, remember what I told you about climbing up the wall? Remember when I'm telling you about
right, because B is still there. Sorry, okay, yeah, because
right, when it's okay because you just see it this morning, okay?
Yeah.
It's okay. You're learning how to apply, and that's a good thing. Don't beat yourself down, okay?
Thanks.
So this will be equal to AY because it's going upwards. 300 is going downwards. Minus 600 is going downwards. Plus by 576.923 times 10 to the power 3. So this will be equal to 0. Okay. So when there's a case, you can calculate AY is equal to 300, 600 minus 576.923 power 3 is equal to 323. I get 323. Okay. 0.077 times 10 to the power 3 Newton, and it's positive, is correct. So what we assume down here is valid. Okay. So you can see the procedure is not pretty standard. The procedure is straightforward, right? It's the analysis, okay, whether what load apply in what section, that is where it's not difficult. It can seem confusing. Okay. Now we are going to do one example. Any questions so far before I go on? Anyone? Any questions so far? No? Okay. So I'm going to go through an example 1 and like the one of the student point out, what if it's horizontal? Okay. Example number 1.
Sir, I got 329. You got 32 for AY.
323.007. Did I write a number wrongly? 576.923, correct. Okay. Can you check your calculation or tell me if I'm wrong?
I just did it twice. 576, not 570. Sorry.
Okay. Okay. So let's look at example number 1. Okay. So we are given. So as I say, you can probably get this. Okay. Okay. So the composite bar consists of a 20 millimeter diameter steel A36 segments from A to B. Okay, A to B steel. Then a 50 millimeters red brass CD. Okay, DA to CB. Determine the average normal stresses in each segment due to the applied load. Okay, you know what? What I'm going to do is I'm going to teach you. I'm going to demo things twice. Okay, I'm going to go into the solution manual. Okay, and I'm going to show you what I mean by don't always look at the solution. What are the key checkpoints? I'm going to demo that in front of. I'm going to demo that with you, and I'm going to deliberately do the opposite. Opposite to what the solution manual does. Okay, I'm not going to follow the solution manual, and our answer should be the same. Okay, so this is the solution manual. I take questions from here, but I modify them as you all can see what I've done in your quizzes. Okay. Okay, so this is the solution. Okay. And I'm going to. Okay, so this is too big. Some of you are like, oh, it's a solution. Yeah, it's a solution, unfortunately. Okay, so this is the solution manual. Okay, I did not do this. This is from the solution manual. So what the solution does is the solution does the same thing like what I've taught you guys. Okay, you let it grow and then you push it back. Okay, and then divide things. So this is what you see in a solution manual. Okay. The loads, you will not know why. It can be confusing. So, but what I want to highlight is the solution menu remove the support at where? At point D. Okay, so you can see down here at point D, they remove the support. Okay, then one student asked me, what if, not one student, I told one student, right? I'm going to check, if you remove from the opposite direction, the answer should be the same. Okay, and I'm going to do that. Okay, so for our solution, so this is what you see in the solution manual. The key thing about the solution manual, the key feature to look for is this. This number and this number has to be the same regardless whether regardless whether you remove support at point D or the support at point C. Okay, and then they have things like that. Sometimes you can get confused. Why do they consider this and that? Okay, so we'll go on. You can get confused. So what I'm going to do now, I'm going to do the direct opposite. Okay, and what do I mean by direct opposite is I'm going to copy the diagram here. Okay, I'm going to go to the next page. Okay, what I'm going to do is we are going to remove